Everything you have ever done, thought, or built will be completely erased. Not metaphorically, physically, thermodynamically, geologically erased. The hard drive holding your photos will decay within decades. The paper holding your writing will rot within centuries. The stone bearing your civilization's name will dissolve within millions of years. And then the tectonic plate carrying that dissolved stone will be dragged into Earth's mantle at 2500 degrees Celsius and completely liquefied. Every artifact, every fossil, every chemical signature, vaporized. You assume human civilization will leave a permanent mark on this planet. It won't. The laws of thermodynamics and geology have placed a hard ceiling on how long information can survive. Not a soft limit that future technology might breach, a physical limit, enforced by entropy and plate tectonics, with no exceptions. In roughly 300 million years, the geological record will contain no detectable trace that humans ever existed. Earth will reset as if we never happened. This is what the physics demands. To understand why, you need to understand what information actually is. In 1948, Claude Shannon at Bell Telephone Laboratories published a paper that redefined information as a physical quantity. Shannon showed that information has a measurable relationship to entropy, the tendency of ordered systems to collapse into disorder. Ludwig Boltzmann formalized entropy in the 1870s. Heat flows from hot to cold, never the reverse. Organized structures spontaneously disintegrate into chaos. Information, precisely ordered physical states, is governed by the same law. In 1961, physicist Rolf Landauer at IBM proved something remarkable. Erasing information is not a conceptual act, it is a thermodynamic one. Deleting a single bit of data necessarily generates heat. Information is physically embedded in the states of matter. Destroying that order releases energy back into the universe. Every crumbling inscription, every corrupted file, every faded photograph is thermodynamically inevitable. The universe is not neutral on the subject of memory. It actively reclaims borrowed order back into chaos. Magnetic hard drives, the primary repository of most digital data on Earth, have a data retention lifespan of 5 to 10 years without regular refreshment. The physical drive itself may survive 50 years before corrosion renders it unreadable. Flash memory, the solid-state storage in your phone, retains data for perhaps 10 years without a power source. Without regular power cycling, electrons trapped in flash cells slowly leak away. The data evaporates, bit by bit, into electrical noise. Paper, the medium that preserved civilization for millennia, has a lifespan measured by its acid content. Modern wood pulp paper, introduced in the 1840s, contains lignin and acid byproducts that cause it to crumble within decades. Medieval parchment, made from dried animal skin, survives far longer. Some manuscripts remain readable after 800 years. The Dead Sea Scrolls, written on animal skin and stored in cool, dry caves, survive 2,000 years, a remarkable anomaly, not a rule. Stone seems permanent. The pyramids at Giza are 4,500 years old and still standing. The cuneiform tablets of Sumer are 5,000 years old and still legible. But stone erodes. Limestone dissolves in slightly acidic rainwater at roughly 1 millimeter per century in temperate climates. In 1 million years, most surface inscriptions are physically gone. In 100 million years, even the rubble is chemically assimilated into the landscape. But weathering is not the deepest threat. The deepest threat is plate tectonics. Earth's crust is broken into dozens of tectonic plates, constantly moving, colliding, and sliding beneath one another. At subduction zones, the deep ocean trenches ringing the Pacific, oceanic crust is dragged down into the mantle at 2 to 15 centimeters per year. Temperatures at depth reach 1,200 degrees Celsius. Everything on that descending slab, rock, sediment, fossil, artifact, chemical signature, is completely liquefied. The average age of oceanic crust today is only 60 million years. No oceanic crust older than 200 million years exists anywhere on Earth. The ancient Tethys Ocean, which once separated Laurasia from Gondwana, is entirely gone. Swallowed by subduction, without a trace of its floor remaining. The exception, at first glance, seems to be continental cratons. Cratons are the ancient, stable cores of continents, thick, rigid slabs of Precambrian rock too buoyant to be easily subducted. The Superior Craton in Canada contains rocks 4 billion years old. The Pilbara Craton in Western Australia preserves rocks 3.5 billion years old, among the oldest known surface rocks on Earth. Those ancient rocks contain microfossils of early life, readable after 3.5 billion years. If rock can survive 4 billion years, Why not human artifacts? Because cratons preserve deep crustal rock, not surface material. The Pilbara's ancient microfossils survived because they were buried under kilometers of later sediment and locked in chemically stable chert matrices. No human artifact will be buried under kilometers of protective sediment in any useful time frame. Surface structures erode. Buried artifacts are destroyed by groundwater, chemical weathering, and bioturbation, the physical churning of sediment by organisms. The rare exceptions, like the Burgess Shale of British Columbia, required extraordinary geological luck. Cambrian organisms were captured 508 million years ago through rapid burial in anoxic, fine-grained sediment with no subsequent heating. Even then, what survived was chemistry, carbon impressions in rock, not the organisms themselves. Survival required burial, cold, anoxic chemistry, and geological stillness, a combination almost impossible to engineer deliberately. In 2018, Gavin Schmidt, director of NASA's Goddard Institute for Space Studies, and astrophysicist Adam Frank at the University of Rochester published a paper in the International Journal of Astrobiology. They asked a question no one had formally posed. If an industrial civilization had existed on Earth 100 million years ago, what traces would remain today? They called this the Silurian Hypothesis. No buildings, no roads, no machines. All surface structures would be completely eroded within tens of millions of years. What might remain is a thin geochemical anomaly in the sedimentary record, unusual isotope ratios, and elevated metal concentrations. Exactly the kind of subtle signal we ourselves are currently creating, but one easily dismissed as a natural geological event. Schmidt and Frank concluded, "We probably could not detect a prior industrial civilization, even if one had existed. The geological record is simply too destructive over those timescales." Even before geology gets involved, information has another enemy: quantum mechanics. Cosmic rays, high-energy particles streaming continuously from space, strike storage media and spontaneously flip individual bits. This phenomenon, called bitrot, affects every storage medium on Earth. CERN found in 2007 that standard computer memory experiences roughly one spontaneous bit flip per 256 megabytes of RAM per month. Over years and decades, these flips accumulate, gradually transforming stored information into noise. In space, away from Earth's protective magnetosphere, the rate accelerates dramatically. The Voyager Golden Record, launched in 1977, is made from gold-plated copper, chosen to last 1 billion years in the vacuum of interstellar space. The same cosmic ray bombardment that corrupts hard drives would degrade it significantly within millions of years of surface exposure on a planet. The void is the only archive. Biologists have proposed DNA as a durable information storage medium. Mammoth DNA recovered from permafrost has survived intact for 700,000 years. Researchers at the University of Copenhagen extracted functional genetic sequences from a Greenland ice core in 2021, plant and animal DNA over 1 million years old. But DNA in normal sediment, subject to groundwater and bacterial activity, fragments beyond recovery within centuries. No DNA has been reliably recovered from material older than approximately 2 million years under any conditions. At geological timescales, even DNA is a temporary medium. There is one category of human artifact specifically designed with geological timescales in mind: nuclear waste. The Waste Isolation Pilot Plant in New Mexico stores radioactive material that will remain hazardous for 10,000 years. The designers commissioned a project to warn future civilizations about the site, across those 10,000 years. The Human Interference Task Force, assembled in the 1990s, faced a profound problem. How do you communicate danger when language, culture, and writing will have completely transformed? Their proposals included massive earthwork landscapes, 10-meter granite monoliths, and expressions of horror carved in stone. Even these warnings, designed specifically for maximum longevity, are expected to become illegible within 100,000 years. 1 million years is beyond serious consideration. Plutonium-239, produced in nuclear reactions, has a half-life of 24,100 years, detectable in sediment for hundreds of thousands of years. Iodine-129, a fission byproduct, has a half-life of 15.7 million years. These isotopes, along with the carbon-14 spike from nuclear testing, elevated nitrogen from synthetic fertilizers, and global plastic microparticles, form what geologists call the Anthropocene stratigraphic signal. In 2020, Jan Zalasiewicz at the University of Leicester calculated that this chemical fingerprint could remain detectable in sediment for up to 50 million years. 50 million years. In geological terms, a blink. 66 million years ago was the Chicxulub impact that ended the non-avian dinosaurs. That event is already barely a whisper in the geological record. The Anthropocene layer, 50 million years from now, will be a faint chemical trace, difficult to distinguish from natural variability. At 300 million years, Schmidt and Frank concluded, the geological record becomes essentially opaque. The signal-to-noise ratio of any industrial civilization's traces falls below the threshold of detectability. 300 million years ago was the late Carboniferous, the age of vast coal swamps, giant dragonflies, and the assembly of Pangaea. We have found fossilized tree roots and insects preserved in amber from that era. But that record is fragmentary, biased toward exceptional preservation, and represents a tiny sample of what actually existed. No industrial civilization from that period could be distinguished from the natural record. Not because they did not build, but because the geology consumed the evidence. Even the radio signals Earth has broadcast since Marconi's first transmission in 1895 are not preserved. They dilute across light years, following the inverse square law, until they dissolve into background noise. Sit with that for a moment. The most durable artifact you can conceive, stone monuments, radioactive isotope signatures, deep geological repositories, survives at most tens of millions of years. Against the 4.5 billion year timeline of Earth, that is vanishingly thin. Against the projected lifespan of the Sun, another 5 billion years, it is essentially nothing. Which raises a question that cuts deeper than academic concern. If physical evidence of civilization cannot survive geological time, what is the point of building anything? That is the wrong question. You do not love someone because they will be remembered in 300 million years. The capacity to experience meaning is not diminished by the thermodynamic impossibility of infinite preservation. But the data decay problem does force a more practical question. Within the timescales where preservation is possible, are we doing enough? The Library of Alexandria burned, not by a single catastrophic fire, but gradually, through neglect and institutional collapse, over centuries. It had no off-site backup. The Maya codices, tens of thousands of books recording centuries of astronomical knowledge, were burned by Bishop Diego de Landa in 1562, leaving only 4 survivors. The accumulated scientific knowledge of the Islamic Golden Age was disrupted by the Mongol sack of Baghdad in 1258. We are better now, digitally distributed, redundantly backed up, globally networked. And yet, 100% of current digital preservation relies on continuous, active maintenance. There is no passive, self-sustaining archive for human knowledge. Every library requires power, staff, funding, and institutional continuity to survive. The Long Now Foundation is building a 10,000-year mechanical clock inside a mountain in Texas, a monument to long-term thinking. The Memory of Mankind project is etching human knowledge onto ceramic tablets stored in salt mines in Austria, targeting 1 million years of survival. These are beautiful efforts. At 300 million years, they are indistinguishable from dust. The universe does not offer permanent storage. Every civilization that has ever existed, or ever will exist, faces this same arithmetic. The Milky Way alone contains 100 billion stars, most with planets. If life is common, and the chemistry suggests it should be, this erasure is happening everywhere. Civilizations rising and falling in silence, their records unreadable within geological time. The Fermi paradox, the question of why we detect no signal from intelligent life, may have a thermodynamic answer. Not that intelligence is absent, but that existence does not leave a permanent signal. The question is not whether we will be erased. We will be. The question is what we choose to build in the time the geology allows us. The reaching matters, even if no one keeps the record.